Good afternoon, my dear students. We're back again for CHE 311 Physical Chemistry 2, Module 2. Of course, Module 2 is also divided into Module 2.1, 2.2, and 2.3. And Module 2.1, Statistical Mechanics. I still remain Professor Engineer J.C. Igwe. Now, for this lecture, we're going to look at introductions, postulates of statistical thermodynamics. We'll look at macrostates and microstates. Then we'll look at some illustrations and conclude. This is by introduction. Statistical thermodynamics introduces in a qualitative way the concept of statistical mechanics in order to illustrate how properties of chemical system can be interpreted in terms of microscopic properties. So we're looking at macroscopic properties. Macroscopic means bulk. That is what we can see. Micro is very small. You know, when you say something is micro, means possibly we can't see with our eyes. So that is what is happening inside. In fact, I tell students that micro is like spiritual, while macro is physical. You know, those of us who are, I don't know whether to use the word fanatics or fanatics. You know, when they say before something happens in this physical, it must have happened in the spiritual realm. So before you see the bulk properties, the macroscopic properties depends on what is happening in the microscopic, you know, spiritual realm, while macroscopic is physical. So statistical thermodynamics tries to show how the knowledge of energy levels of molecules can be used to account for the properties of matter involved. So we try to look at the knowledge of energy levels of molecules at that microscopic level and account for what is happening in macroscopic or bulk properties. Statistical thermodynamics provides an additional interpretation of concept of entropy. You know, for those who will go higher, the higher courses, you will understand what we mean by interpretation of this concept of entropy. Statistical thermodynamics take advantage of the fact that molecules are very numerous, and average properties of a large number of molecules can be calculated even in the absence of any information about specific molecules. So when you have 1 million molecules, you will not come and start looking for the behavior of individual molecules. Just like in a class, if we have, you know, those in biochemistry, maybe about 200, and also chemistry close to 100, into chemistry and all that, we can decide to look at the behaviors as per the class, not trying to look at the individuals. We can say, these 400 level biochemistry students are very crazy. These 400 level biochemistry students are very nice. You know, if they are nice students, it does not mean that there is no bad student there, but we're looking at the average behavior of all the students there. So we're giving them a pass mark because the average behavior is good. That's what it means. We're looking at average, you know, behavior of the molecules, not individual molecules, because we have a very large number of molecules. Thermodynamic properties of bulk samples and average behavior of large number of molecules. Yes. Thus, equilibrium properties of molecules can be interpreted from two viewpoints, macroscopic and microscopic. The macroscopic property is the behavior of large number of molecules in terms of our pressure, volume, and temperature behavior, and of course, exchange of heat and water. Thermodynamics builds a link or bridge so that we can go from the bulk properties to the microscopic world of atoms and molecules. Microscopic properties define the system in terms of behavior of individual, which involves the knowledge of structure of the system and knowledge of the mechanism by which they interact. Now, kinetic theory explains pressure, heat capacity, if you remember all these, energy, heat capacity, and so on. But it fails to explain variation of heat capacity with temperature for complex gas molecules. Therefore, ideally, we would like to be able to predict thermodynamic properties from knowledge of individual molecules and the mechanisms of interaction. And this is what statistical mechanics does. Look at it. Look at our link here, microscopic, quantum mechanisms, molecular interactions. Through statistical thermodynamics, we can now get the bulk or equilibrium properties. Postulate of statistical thermodynamics. Now, a number n, capital N, of identical entities is called an assembly. Now, the entities may themselves be identical assemblies of particles, in which case one has an assembly of assemblies, and this is called an ensemble. So you can come in a class, in that class becomes a group that is an assembly. Now, inside this class, if you have another group of students or another groups that are, you can call reading groups, then it means that we're now having smaller groups in a larger group, and then we call that larger group an ensemble, that is an assembly of assemblies. And we'll particularly have two postulates of statistical thermodynamics. The first postulate says, as the number of system n in the ensemble becomes very large, the ensemble average of a mechanical variable approaches the long-time average of that variable in the real system. The second postulate says the system in an ensemble representative of an isolated thermodynamic system are distributed with equal probability over all possible quantum states. And this is called the concept of equal a priori probabilities. That is, all energy states have equal ability of being occupied. None is having a preferential treatment, kind of. That's what is saying, equal probability, equal a priori probabilities. Macrostates and microstates. We will be able to differentiate between microstates and macrostates. If the distribution of the particles of the system amongst energy is known, the macroscopic properties of the system can be defined. Therefore, a central problem of statistical thermodynamics is to determine this distribution. You see, statistical thermodynamics wants to determine the distribution. For instance, in the class, people are making noise. We will now ask a question. Is the sitting arrangement affecting the noise? For instance, if we remove Mr. A and Mr. B and exchange them, will the noise reduce? If we bring Mr. A and Mr. C together, so that arrangement in that class that generates that noise, we now have to look at 2 points, whether the particles are distinguishable or indistinguishable. For us human beings, it's easy to distinguish. But imagine a situation where we cannot distinguish maybe Emeka from David. So which means even if you exchange their positions, you will not even know that you have exchanged because you cannot distinguish them. But when you distinguish them, that is a different ballgame. So we'll see that distinguishable and indistinguishable gives us different types of statistical mechanics. Suppose the assembly is a sample of gas and the individual molecules are the particles. Since there is no way in which the molecules can be labeled, the particles are indistinguishable. On the other hand, if the assembly is a crystal, the molecules can be labeled in accord with the position they occupy in the crystal lattice and can be considered distinguishable. You see two examples. If they are gases they are mobile, you may not be able to distinguish them. But if they are solids have fixed positions, you can distinguish them by their position in the crystal lattice. So whether the particles are distinguishable or not, we will now have a specification of number of particles at the level so that we'll have the microstates of the assembly. Now look at, we have tried to show this, the energy levels, then the ones that are degenerate, that is having the same energy, and of course their occupation number. Look at that figure. You will see, now the first one is supposed to have 5, what we have in that E1 there is 5 molecules. Now E2, we have 4 molecules. Look at it, but we have 3 occupation states. In these 3 occupation states, the first one, 2 is occupying there. The other 2 will have 1, 1. Now for E3, look at what we have. we have G, that is the occupation state, equal to 4 of them. Now, but 3 are occupied. There is 1 here that is not occupied. Then here we have 5, but 2 is occupied, 3 is not occupied. This is exactly what we want to look at, whether they are distinguishable or not distinguishable. So if the particles are distinguishable, a specification of energy state of each particle is said to define the microstate of the assembly. That is, we must specify not only how many particles are in each state, but which particles they are. But if the particles are indistinguishable, a specification of total number of particles in each energy state is said to define the microstate of the assembly. So we're looking at indistinguishable particles and distinguishable particles. So now, suppose that the particles in the figure are distinguishable and are labeled as A, B, C, and that in the level 4, particle A is in state 3. Now we're trying to now picture a situation where we can change the positions of these particles, and then we know what that will be. If there is more than 1 particle in a given energy state, an interchange of the order of which these letters designating the particles is written is not considered to change it, you see. So when we write either AB or BA, if they are indistinguishable, then it doesn't matter. But if they are distinguishable, then of course there will be a change. So as an illustration, let us consider distribution of energy between atoms in one-directional crystal lattice, in which atoms will be regarded as simple harmonic oscillators. The atoms will be regarded as very loosely coupled. We can also distinguish the atoms by means of their location, since all motions can be regarded as quantized. We assume that the total energy is made up of a definite number of quanta. Now we'll use this as an illustration. Consider the distribution of 3 quanta of energy in lattice of 3 atoms. What is the total number of microstates? Now I'm sorry this video might take a little long, but then let's see how it goes. Now consider this distribution of 3 quanta between 3 atoms. So we're going to look at the possibilities. Let me explain this. Imagine where 3 students are going to share 3 oranges. That's what it means. Now the first possibility, which is this first one, let atomic positions be designated A, B, C, that is the oranges. Now one possible configuration is known as 300. Now this 300 means that one student takes 3 of the oranges and the other 2 students will be left with none, that is 00. And if you look at this distribution, it means that it can happen in 3 places, 3 possibilities. First is, let us name these students. One is, which names are we going to use now? What is the name of this course reps? I can't even remember their names. But let's assume, let's use the girls now. One is Ijoma, the other one is Jennifer, and then the 3rd person is what? Okay, let's use Miracle. So Ijoma, Jennifer, and Miracle are sharing 3 oranges. It's possible that Ijoma can take the 3 oranges, which means Jennifer and Miracle will be left with no orange. That's 300. It's possible that Jennifer can take the 3 oranges. Then Ijoma and Miracle will be left with no orange. And also it's possible that Miracle can take the 3 oranges and Ijoma and Jennifer will be left with no orange. So that's what we call 300, and that gives us 3 possibilities. If you look closely, you see the dots. Let's assume that A is Ijoma, B is Jennifer, and C is Miracle. So now A has taken 1 dot, therefore B and C will have to be at 0, 0. The next possibility, A that took 1 dot, the 3 is no longer taken. So it's B that is now taking 3. Look at the dots there at B at 3. Then A and C will now be 0, 0. Now the 3rd one is C, will take 3, and A and B will take 0, 0. That is configuration of 3, 0, 0, which gives us 3 possibilities. Now the second one is 210 configuration, and this gives us 6 possibilities. Look at it. Ijoma can just take your time, take a piece of paper and do this, and you understand. Ijoma can take 3. Jennifer will take 1. Miracle will be 0. That's 1. Now, Jennifer can take 2. Ijoma will take 1. Miracle will take 0. Now, Miracle can take 2. Jennifer will take 1. Ijoma will take 0. These are the things we have done here. Look at the dots. The first one here, A is 2, B is 1, C is 0. The next one here, A is 2, B is 0. Initially, B had 1 here, but B is now 0, and C is 1. Here, A is 1, B is 2, C is 0. So this gives us 6 possibilities. Now the last is 111. That is 3 oranges where they will now share it. Ijoma takes 1, Jennifer takes 1, Miracle takes 1. So there's no way you can interchange. Even if you interchange it, it's still 111. Change it whichever way, it's still 111. So that one gives us only 1 possibility. So that the total number of microstates, the total number of possibilities of this distribution will be, the first one is 3, second one is 6, and the last one is 1. That will be 3 plus 6 plus 1, which is equal to 10. From statistical point of view, each of these 10 microstates is assumed to be equally probable. Remember the equal a priori probability. So these 10 microstates are equally probable. The total number of microstates is referred to as the thermodynamic probability. And that's what we'll be looking at in the next module, thermodynamic probability. In fact, we'll also use that thermodynamic probability to also the equation for thermodynamic probability, and then work this and see that we'll still get the same answer without going through all these tables we have drawn. Because if the quantum of energy increases and the number of atoms increases, it will become confusing to start drawing all these kind of boxes or tables. Of this module 3, is it 3.1 or 2.1? This is module 2.1. So we have introduction to statistical thermodynamics, postulates of statistical thermodynamics. We have looked at microstates and macrostates, and then the energy levels and their degeneracy, and we also used illustration to show what we have done. So I hope to see you in the next class. Thank you very much.